and pass to the speaker, Lindsay Oftelie.
Hello.
Hello. So I think you can share your screen, and in the meanwhile, I introduce you. So Lindsay Oftelie got her master in physics at the University of Chicago with Jonathan Simon in 2014, and in 2020 she got a PhD in physics at the University of Southern California in Los Angeles under the direction of Aihiro Nakano, and the title of the thesis was Controlling Electronic Properties of Two-Dimensional Quantum Materials, a Simulation at the Nexus of the Classical and Quantum Computing Eras. Then a first postdoc at Lawrence Berkeley National Lab, and since a couple of years she's a Marie Curie Fellow at the CNR Institute of Nanoscience in Pisa, and the title of her presentation is Dynamic Cooling on Contemporary Quantum Computers. Please, Lindsay, 25 minutes. Thank you.
Okay, thank you very much for the introduction, and thank you to the organizers for inviting me to give a talk at this seminar series. I'm excited to talk to you today about work I've been doing on cooling qubits on quantum computers. So since I'm going to assume this isn't a fully quantum audience, I'll give a very, very brief introduction to quantum computers. So whereas classical computers are based on classical bits, which can exclusively be in either the 0 or the 1 state, quantum bits or qubits can actually be in both a 0 state, a 1 state, any combination between the two states, also with any phase. So a qubit can be in an infinite number of states, and this can be represented by the points on a unit sphere, as shown here. Now, the two main quantum effects that qubits have are superposition, which is when the qubit can kind of be in both two states at once, shown here. And this gives rise to a kind of quantum parallelism, where you can run a program on the qubit being in both the 0 and the 1 state at the same time. If you have more than one qubit, you can also have entanglement, which is a kind of correlation between two qubits, which has no classical counterpart. And this entanglement allows you to kind of store information in the relationship between two qubits. So you can store information in qubit 1, you can store information in qubit 2, and you can also store information in the relationship or the correlation between the two qubits. And so quantum parallelism, arising from superposition, allows us to kind of speed up computation with quantum computers, and entanglement kind of allows us to store more information with quantum computers. And so these two main quantum features is what gives quantum computers an advantage for certain problems. So there are actually a number of available quantum computers today, and they're based on a number of different technologies. It is not clear yet what the leading implementation of a qubit is, right? A qubit can be any physical two-level system that obeys the laws of quantum mechanics. So some companies such as IBM, Rigetti, and Google have chosen to build quantum computers that are based on qubits made from superconducting circuits. So each qubit is represented by one superconducting circuit. Companies like IonQ and Honeywell base their quantum computers off of trapped ions. Companies like Pascal use neutral atoms for their qubits, and companies like Xanadu use photons for their quantum computers. And so each of these has their different pros and cons, and at this point it's unclear who's going to come out ahead. But no matter what implementation you use for your qubits, we can kind of talk about how you run quantum computation at a more abstracted level through the use of quantum circuits, which are basically a set of quantum logic gates that you perform on your qubits. And we can represent quantum circuits with a quantum circuit diagram shown here. Each wire represents a qubit. Moving from left to right represents moving forward in time. And a box over a wire represents acting a gate on that qubit, or a set of gates on those qubits. So at a high level, generally, we assume that our qubits are all served to us in the 0 state, and I'll come back to that in a little bit. We perform some set of gates on those qubits to initialize our qubits into the desired initial state for our given problem. We then usually want to evolve our system or propagate our state in some way by applying some other set of gates. And finally, there are usually some set of gates you need to perform before you measure your system, which allows you to kind of measure different observables of the qubits. At a lower level, a quantum circuit might look something like this, where these kind of high-level blocks are broken down into the individual single and 2 qubit gates that are actually physically implemented on your qubits using electromagnetic pulses. Single qubit gates will rotate a single qubit in some way, and 2 qubit gates are what are responsible for generating entanglement in your system. Okay, so as I said, we are going to assume when we build our quantum circuit that all our qubits start in the 0 state. Now, if the qubits were actually to start 100% in the 0 state, this would effectively mean that they are at 0 temperature. And the third law of thermodynamics tells us that we cannot reach 0 temperature. So what this means is that our qubits are not served to us 100% in the 0 state, but rather mostly in the 0 state and some tiny percentage in the 1 state. And the higher that percentage is, the more error we will see propagate in our execution of our circuit, because our circuit was designed on the assumption that our qubits start in the 0 state. So to reduce error in quantum computation, one of the major things we need to do is get our qubits as close to the 0 state as possible initially. And we can do this by cooling our qubits. And that is why I am interested in cooling qubits. The more we cool them, the closer to 100% in the 0 state they get. So experimentalists have worked very hard to use kind of direct physical cooling techniques to get our qubits as cold as possible. And they've succeeded in getting qubits to very low temperatures on the order of 15 millikelvin using lasers and magnetic fields. But these direct physical methods are quite resource intensive, and they also have their limitations due to feasibility. So scientists then started to wonder if we could use kind of effective cooling techniques to cool our qubits using logic gates. And the first such method of this computational cooling was known as dynamic cooling and was put forward almost 25 years ago. And in this setup, we assume we have a system of n qubits at some all at the same initial temperature. We're going to apply a global unitary to the entire system, which will have the effect of cooling our target qubit while heating up the auxiliary qubits. And the assumption here is that we'll use our cooled target qubit for computation and throw away our heated up auxiliary qubits. Now, this is a closed system, which means that the entropy cannot decrease. And so this puts a bound on the coldest that we can get this target qubit, known as the Shannon bound. And at the time that dynamic cooling was proposed, the quantum computers in existence were NMR quantum computers, nuclear magnetic resonance quantum computers. And these quantum computers had qubits at very, very high initial temperatures. And so using the assumptions of the Shannon bound, they did some back of the envelope calculations to estimate how cold you can get this qubit as a function of the number of auxiliary qubits you're using. And they found that in this high initial temperature regime, cooling was limited to at most 1 over the square root of n. So this is very poor scaling with number of qubits. Since these NMR quantum computers started at such high initial temperatures, they were seeing that they were going to need on the order of tens of thousands of qubits to just cool a single qubit down to a reasonable level. So this wasn't going to work. And they thought, how can we beat this Shannon bound? Well, because the Shannon bound applies to a closed system, they thought, let's open the system up. Let's allow our qubits to talk with the environment, interact with the environment. So this led to the development of what's known as heat bath algorithmic cooling. And this proceeds in two phases. You first do a phase of dynamic cooling, as before, but now you open up your system. You allow your heated up qubits, a subset of heated up qubits, which are called the reset qubits, you allow them to rethermalize with your bath and reintroduce them to your system. And then you do another round of dynamic cooling. And you can cycle through these two phases, and this is essentially going to pump heat out of your system into the environment. And in this way, you can cool your target qubit well below the limit that we saw in just closed system dynamic cooling. Now, an implicit assumption here is that you need two species of qubits. This is because the target qubit, the one you're going to use for computation, you want this to have a very long relaxation time. You want it to hold its information for as long as possible because you need it for computation. On the other hand, the reset qubits, you want them to have a very short relaxation time so that they will rethermalize with the bath quickly, allowing you to do multiple steps of algorithmic cooling. And this was okay with NMR quantum computers, which had qubits in the nucleus and the electrons. The nuclear qubits had very long relaxation times and could be used for the computational qubit, your target qubit that you're going to cool. And the electrons could be used for your reset qubits. These rethermalize with the bath very quickly. They have short relaxation times. Okay, so this was the story as of 20 years ago. And then not much really happened more with computational cooling. We fast forward 20 years, and we now have a very different set of quantum computers available to us now. Now, our quantum computers all have identical qubits, a single species of qubit. And so this immediately knocks out the ability to use heat bath algorithmic cooling, which required two species of qubits. What we do get, though, is that now our quantum computers are initialized at very low initial temperatures, unlike the NMR quantum computers. So we thought, let's re-examine dynamic cooling, but with the assumption that we're starting at a low initial temperature and see if things look better. So let's review this, the setup of our system. We have our N qubits that are all initialized at the same initial temperature beta, inverse temperature beta. And we can, from this initial temperature, derive the initial probability of our target qubit being in the 1 state. So this should be small because we're starting at a low initial temperature. We apply our cooling unitary, and the effect is to cool our target qubit at the expense of heating up the others. And our target qubit will have a final probability of being in the 1 state, which since we're cooling, this will be smaller than the initial P1. And this P1 prime has an associated final inverse temperature beta prime. So the problem of trying to find the maximum amount of cooling is equivalent to trying to minimize this P1 prime, this final probability of our target qubit being in the 1 state. And so we used some results from quantum thermodynamics, specifically based on ergotropy, which is the maximum work you can extract from a driven quantum system. And this enabled us to derive an equation for the minimum P1 prime based on the initial P1 and the number of qubits n. When we derived this for odd n, we actually found that for even n, it is the same, you achieve the same amount of cooling for the odd n 1 integer lower. So if you have an even n, just subtract 1, and you can use this same equation to discover how much cooling you get for a given number of qubits. Now, as I said, we can associate this initial probability of the target qubit being in the 1 state with an initial temperature, and likewise the final probability can be associated with the final temperature. So plugging in these transformations, we get an equation for the final temperature of our target qubit given the initial temperature and the number of qubits n. And if we plot this, we see something very interesting. This plot here is showing the initial temperature on the x-axis versus the final temperature on the y-axis. This black dashed line plots t equal to t prime. Okay, so nothing's happening. This is just to guide the eye. And it says that anything below this line means that our system is being cooled. The different colored lines are for different system sizes. S is the number of qubits divided by 2. So this is for 4 qubits, 8 qubits, 16 qubits, etc. Now, in the high initial temperature regime, you see that as you add more qubits, you're not getting a whole lot more cooling. And in fact, if you look at how T prime, the final temperature, scales with initial temperature, it indeed scales as 1 over the square root of n, which they found back in the day, and they were not happy with. But look at this interesting transition as you go to lower initial temperatures. Now in this regime, you can clearly see that as you add more qubits, you're getting a lot more bang for your buck. You're getting a lot more cooling power from adding more qubits. And indeed, in this regime, the final temperature, T prime, now scales as 1 over n. So we see a dramatic increase in the amount of cooling you're getting as you add more qubits. So dynamic cooling, therefore, is much more effective in the low temperature regime, which is where our current quantum computers are at today. In fact, if you look at the initial temperature of most current quantum computers, it falls in this area. So you see it's really at the start of this kind of more efficient, more effective cooling regime. So this is great. Dynamic cooling should indeed be re-explored for our current quantum computers. Furthermore, we looked at the minimum amount of work per qubit required for cooling, for dynamic cooling, and we found that dynamic cooling is also much more efficient, meaning it uses less work in the low temperature regime. In the low temperature regime, the minimum amount of work decreases exponentially with decreasing temperature, whereas it decreases much more slowly with temperature in the high temperature regime. So dynamic cooling is more effective, it's more efficient. This sounds great. We should start using it immediately on our current quantum computers. The problem, of course, comes with the implementation. While theory says that as we add more qubits, we should, in theory, get more cooling. Unfortunately, as we add more qubits, the circuit to implement this cooling gets larger and larger. And unfortunately, it looks like the size of the circuit increases exponentially with the system size. So the larger a circuit is, the more room there is for errors to add up, right? Every gate you apply has an associated error rate that comes with it. The longer it takes for the circuit to run, the more time there is for your qubits to decohere. So longer circuits are bad. And we see this, how this plays out, by simulating dynamic cooling on a noisy quantum simulator. So this is a program that runs on a classical computer, but it emulates the performance of a noisy quantum computer. And you do this by defining a noise model. In my case, I defined a noise model that's parameterized by a single parameter p, which is the effective error rate of my noise model. And so here I plot how dynamic cooling performs on a noisy quantum computer as I scale this error rate across, which is shown on the x-axis. The final temperature is shown on the y-axis, and I do this for 2 initial temperatures. Let's focus first on the initial temperature of 15, shown by this black dashed line. Now, the different colors are different sized systems, and at very, very small error rate, so on basically a noise-free quantum computer, we see exactly what we expect. As you increase n, you get increased cooling. You see that using 3 or 4 qubits, results in the same amount of cooling. 5 and 6 qubits results in the same amount of cooling, 7 and 8, etc. Right? We said that we need to, if we just go to an even number of qubits, that will be the same amount of cooling as 1 and lower. But as we increase the error rate, these lines split. And that's because the circuit for the higher number of qubits is larger and will incur more error. And so what this tells us is that even though theoretically taking n to infinity should be what we want to do, right? That will continually increase our cooling power. Unfortunately, for a given level of noise, there will be an optimal n that you'll want to use, because going to a higher n will make the circuit too long, will incur too much error, and could result in your qubit, in fact, being heated instead of being cooled. Now, I showed two different initial energies to show that, initial temperatures to show that the onset of when noise starts to have effect is actually later for the higher initial temperature. So what this says essentially is that the lower temperature your system starts at, the more affected it is by noise. Or conversely, the higher the initial temperature, the more robust it is to noise. So this looks bad. Circuits grow exponentially with size. We're not going to be able to go to very high n in this regime. So we proposed a kind of way to combat this, which we call suboptimal dynamic cooling. So in suboptimal dynamic cooling, we're gonna give up a little bit of cooling power, and in return, we're going to dramatically reduce the complexity of our circuits. So in the suboptimal cooling we derived, what you do is you divide your system into clusters of little n, in this case 3, and you perform R rounds of dynamic cooling. So consider we have 9 qubits. We could just perform optimal dynamic cooling on 9 qubits. This will result in a very large circuit. So instead, we can do suboptimal dynamic cooling, where we just perform dynamic cooling within each of these smaller clusters. And this will result in 1 qubit in each of these clusters being cooled. And then in the second round, we perform dynamic cooling with the cooled qubits. And this will result in a further cooled qubit. Now, the final temperature of this qubit is going to be a little warmer than if we just performed optimal dynamic cooling on all 9 qubits. However, the circuit complexity of this suboptimal dynamic cooling is dramatically reduced. Instead of performing a 9 qubit cooling circuit on all the qubits, we just performed 1, 2, 3, 4 circuits on 3 qubits. And because the circuit size grows exponentially with n, performing 4 3-qubit circuits is much, much less complex than 1 9-qubit circuit. And this can be very nicely shown, again, with this noisy quantum simulations. You see that if we just did optimal dynamic cooling with n equals 9, we achieve the best cooling, right, the lowest final temperature, but it's very quickly affected by noise. And at even quite small error rates, it starts heating the qubit instead of cooling it. On the other hand, this dashed dotted line shows the results from the suboptimal dynamic cooling. And you can see that we've given up a little bit of cooling power. Our final temperature is not as low as it could be, but look how long it remains robust to noise. And this is because the circuit size is dramatically reduced. And it performs quite well. You can see that it even cools more than optimal cooling with 5 qubits. Okay, so the last thing I'll talk about is a demonstration of dynamic cooling on a real quantum computer. We tried running this on the IBM quantum computer, which uses superconducting circuits for qubits. And I attempted to just do dynamic cooling with 3 qubits. And what I did was, the chip on the IBM quantum computer has 127 qubits on it. So what I did was select 12 different groups of 3 qubits, and I performed separate kind of dynamic cooling experiments in each of these 3 qubit clusters. I ran an initial calibration circuit to estimate the effective initial temperature of the target qubit in each of these clusters. And right, because it's arbitrary how I label my clusters, I decided to label my clusters in increasing order of their initial temperature. So this black line is showing the initial temperature of my different clusters. I then performed dynamic cooling in each of the clusters and measured the temperature again. And this is what I found for the final temperature after cooling. And you can see that in 11 out of the 12 clusters, unfortunately, the circuit heated up my system. And this is just because noise on current quantum computers is very, very high still. They do not perform very well, unfortunately. However, on the last cluster, I did actually succeed in cooling the qubit. The final temperature was lower than the initial temperature. And I'll point out that it's not surprising that this only worked for the qubit that was initially at the highest temperature, because as we saw before, the higher the initial temperature of the qubit, the more robust it is to noise. So this made sense to us. And so we took this to be a good sign. We were able to demonstrate at least once an instance where dynamic cooling worked. Unfortunately, levels of noise on current quantum computers are still too high, but these things come down continuously every year. And so hopefully this will get to a point where dynamic cooling will actually be useful, will actually cool your qubit. And perhaps this shows us that what we should do in the future is kind of calibrate our set of qubits, see which ones are at higher temperatures, and maybe just perform dynamic cooling initially on those qubits before we perform any kind of computation. So I see I'm at my time now, so I'll just finish by saying we developed a programming library called Cool for generating these cooling circuits. So it's open source, available on GitHub if you're interested in playing around with this. So with that, I will conclude and happy to take any questions.
Thank you very much. Thank you, Lindsay. So, are there questions or comments? You can raise hand or just switch on your microphone. Okay, I have one question. I mean, the procedure of dynamic cooling you have discussed, it is independent of the actual type of qubits. I mean, qubits as superconductors or photons. I mean, but your procedure, your recipe is the same for all these, for all different types of qubits. Then you made an experiment on a specific quantum computer, IBM, I think, and
Yes.
so it was superconductors.
Yes.
But do you expect that if you do the same in a different quantum computer, you can obtain different results?
Yeah. So the thing that is the same across any implementation is the actual unitary matrix that represents your cooling. What changes between implementation is how you translate that unitary matrix into a set of gates. Now, on the superconducting quantum computer, for example, you can only perform 2-qubit gates on qubits that are actually physically connected. And so this will have some constraints on how this unitary gets translated into gates. On a different platform, like ion trap, for example, you can perform 2-qubit gates on any pairs of qubits. And so this will kind of alleviate, right? It kind of reduces the constraints. You can perform 2-qubit gates on any pairs of qubits. And so I would imagine that the circuit will actually be shorter or smaller on these platforms. So, right, that a shorter circuit will incur less error. So I would imagine this procedure might work better on ion trap quantum computers, for example.
Hmm. Okay, so next experiment will be on neutral ion.
Yes, we try that next.
Okay. Okay, so no other questions. So I thank again both speaker, Lindsay and Jerome, and thank you to everybody. And also we will see again on the same screen next month for the Young Seminar session of December. Okay, good evening
Thank
to
you.
everybody. Thank you.
Ciao.
Ciao.
Thank you.
Ciao, ciao.